Issue 318 then. What have we got here this week? Let's just scan down to the puzzle to see what he's asking. Oh no, what's this beside it? Thought of the week. Do you think the inventor of the percentage sign, and there it is there, was inspired by watching a glamour model put on a seatbelt? A little bit risque, I think. No, actually, I think he probably just got his knickers in a twist. Right, what's in the puzzle beside it? This week's puzzle. My dad sent me a puzzle like this one which appeared recently in an engineering magazine he reads. It took me longer to solve it than I first guessed it would. See how you get on. And here's a description of it then. Right. Wally is wrapping a present for Isabel. He wants to wrap it with white ribbon as shown in the diagram. Twice around the middle, once around the ends. With 2 meters of white ribbon available, what's the maximum volume of the present? So, here we have the present, the dimensions of it, I'll just call that X, Y and Z. And there are 2 meters of, I've got red ribbon here, I think I'll just change that to 200 centimeters. Now, this is an optimization problem, and there actually are proper techniques for solving optimization problems, but they're a bit lengthy, but I'll have to do them at the end. Because to do it intuitively, you're never quite sure about this. There's 3 sort of intuitive ways that I could think about going about getting the answer. Now, one of them would be this. In terms of X, Y and Z, how many of each would I need to make that 200? Well, X is the distance this way. So as far as the ribbon's concerned, I've got 1 across the top, 1 across the bottom. There'd be 2 lots of X. Y would be the distances going backwards. That's 2 across the top, 2 across the bottom. So there'd be 4 lots of Y. And Z being the verticals, there's quite a lot of them. There's 1, 2, 3, then the other side, and then the 2 in the back, that's 6 of Z. Whatever the dimensions of X, Y and Z are, 2 of X and 4 of Y and 6 of Z have to make 200. If you want to use it all, which I presume you would, to get the biggest volume. But I can simplify that. So it's X plus 2Y plus 3Z equals 100. Now that's going to be important because that limits the values of X, Y and Z. This is what's known as a constraint. There's a constraint equation here. And what you want to do is find the values of X, Y and Z that satisfy this and give the biggest volume. So you've got this constraint and you want to maximize this expression X, Y, Z. Now intuitively there's a few things you can think of. One is, if you add 3 numbers together, if the sum of 3 numbers is some fixed amount, then the maximum you get the maximum product when these numbers are equal. So one thing I could try here would be, maybe I'll get the maximum value of the product when these 3 numbers are equal. So I'll try that when X is equal to 2Y is equal to 3Z. Now I just need to figure what they are. Well, I could put them into this constraint here. So using that constraint, I've got X plus, now 2Y is also X, and 3Z is also X. So that tells me that 3 lots of X would be 100, which means that X is going to be 100 upon 3 centimeters. And then straight away, Y is going to be divided by 2. I could call that 100 over 6, or 50 over 3. And Z will be X divided by 3. Z will be 100 over 9, which would give me a volume of 100 times 100 times 100, so it's 100 cubed, or I could just put it down as a million, over 3 times 6 times 9, which should give me a maximum volume of, it's 162, if you just put in your calculator to get this as a mixed number, 6172 and 61 over 81 centimeters cubed. So that's a possibility. Put it here. V equals 6172 and 68 over 81 centimeters cubed, and that's when X equals, that's 33 and a third, Y equals, and that's 16 and 2/3, and z equals 11 and a 9th. A couple of other intuitive things you could think of, because you know that with cuboids, you know that cubes give you maximum volumes. So I could try a couple of cubey things before I do some proper maths to find this. Well, one cubey thing would be, what if you just made it a cube? If you just made it a cube, then x would equal y would equal z. So what would the sizes of each of these be then? Well, they'd have to fit into this. So back to the constraint. X plus, now 2y's would be 2x's, 3z's would be 3x's, since you've made them all equal. That's 6x's, so x would be 100 upon 6. But then, by the same token, so is y and so is z. I'll just put them down. Y 100 upon 6 and z 100 upon 6. That still fits the constraint. One of them and two of them and three of them make the 100. So what kind of volume would I get from this? Well, this time it'll be 100 times 100 times 100. That's the same as before. But it's a 6 times a 6 times a 6, not a 3 times a 6 times a 9. And a 6 times a 6 times a 6 is 216, not 162. So that's a bigger denominator, so it must be a smaller volume. And it is. If you divide that out, that just comes to 4629 and 17/27. So that's a lot less than 6172. So going for the cube didn't work. Another intuitive thing might be, just thinking along the lines of cubes, well, what if each of these, if you spaced these ribbons out equally, so that each of those 6 parts formed a cube? Would I get the maximum volume that time? Well, that means each of these little cubes would have sides of, now it has to be a cube, so all 3 sides would be the same. That would be 1/3 of x. So 1/3 of x would equal, and that's just half of y, but that's all of z. I would have that then to form cubes in each of these parts. Let's pop that into the constraint and see what values we get out of that. Well, if I call x x, then 2 lots of y, well, what is y to begin with here? Y would be 2/3 of x. So 2 lots of y will be 4/3 of x. Plus, now z is 1/3 of x, but 3z will be 3 times 1/3, so that's another x. That lot should come to 100. So putting that all into thirds, I've got 3 and 3 and 4 is 10. That's 10/3 of x makes 100. So x would be, divide by 10, multiply by 3, that's 30. So back to here. So the y would be 2/3 of that, which is 20. And the z would be 1/3 of that, which would be a 10. And you can quickly check that that's correct for the 100. One of them and 2 of them and 3 of them make 100. But what kind of volume do I get from that? What's 30 times 20 times 10? Well, that's 6,000. Well, it's closer. Better than the other one. Better than a big cube having 6 little cubes, but still not the maximum. So it looks like this could be the maximum. The maximum volume is 6172 and a bit centimetres cubed. Having done that intuitive stuff, what's the proper maths in it then to work out this maximum volume? Well, it's an optimization question. What I've got is, I want to maximise the volume, and the volume is equal to x, y, z. It's got 3 variables in it. There's a constraint, there's a condition that connects them together. You've got x plus 2y plus 3z is 100, so I could replace one of them. I could rewrite z as, and that would have to be 1/3 of, because it'd be 3z equals, 1/3 of 100 minus x minus 2y, which means I've now got the volume equal to x times y times this, which I suppose I'll write as 1/3 of x times y times 100 minus x minus 2y. So this volume is expressed in terms of 2 variables. This takes you into multivariable calculus. This expression here saying if you were to plot x's and y's against v, would actually give you a surface in space. So it's not like the one-dimensional case where it's just a graph and where's the turning points, where's the stationary points in the graph. Here, if you were to plot this, there's the x-axis, the y-axis, and of course you're plotting v as the vertical axis. There's going to be some surface here, and you want to find the highest point in that surface if it's a maximum. You also know that if x is 0, the volume's 0. If y is 0, the volume's 0. There's also a maximum. The biggest x can get to, if y is nothing, the biggest x can get to is 100, and the biggest y can get to is 50. So really, you're only considering this domain. X and y have to be positive, and the limits are 0 and 150. And if you were to plot this function for all the values of x, y, and it provides some surface, which of course must be 0 along here, so it's going to be some sort of pudding shape like a loaf. So you could probably guess that that's going to have a maximum at the top, like a knoll. The other option would be a pit like a depression. But that, since it's coming up, it must be a knoll. Now, I'm not going to go into the various ways of determining the nature of the critical point on a surface. It's just how would you find it in the first place. But obviously there is some sort of surface that goes between the two, some pudding shape. How can you find that point there that sits at the top of it? Well, it's derivatives that do that. And what you do is you have to take the derivatives in two directions. So looking across this hilltop this way, shouldn't actually done that way because that's when x is constant, and that way I'll say at the same time. You'll be at the top, you'll be at the critical point if both those gradients are 0, are horizontal. I'll take this one first. If I look up and down the x direction, that means y is constant. So if I differentiate with that with respect to x, keeping y constant, that's a partial differential. I can only go into so much. That means differentiate it as if x is the only variable because you're holding y constant. Oh, I think before I do that, I don't want to use any product rules. I think I'll multiply this out one last time. That's 100 upon 3xy minus a third of x squared y minus 2/3 of xy squared. That's a wee bit crushed up. So what's the partial derivative with respect to x? So if x is the variable, that would be 100 upon 3y. If x is a variable, it would be 2 multiplied by it, that's 2/3 of just xy. And if x is a variable, that'll be minus 2/3 of y squared. And to be at a critical point, to be teetering on the top, that gradient has to be 0. So it means I can divide out all those 3's. I could also divide out the 2's and just have 50's and so on. But I can also take out a y. So I've got a y coming out of it because they've all got a y in it. And that would leave, taking out all the 3's and the 50, that would be, and a 2 I mean, that would be 50 minus, and that's going to be x minus, and that's going to be y equals 0. Now, the solution to that would either be y equals 0, which it can't be. If y is 0, there's no volume. So it must be this condition that applies, and that says this must equal 0. So that means x plus y must equal 50. Right, there's one condition that must be satisfied. Now let's go along the slope the other way. Looking along in the y direction, straight at the x-axis. So that means moving in that direction, x is constant. So if you take the derivative with respect to y, the partial derivative with respect to y, so x has been held constant, then back to the same expression, I'd have 100 upon 3x minus 1/3 of x squared minus, now for y that'll be 4 upon 3, remember x is just appearing like a constant, xy. And if it is indeed the top point, then that should equal, or a stationary point, critical point, that should equal 0. Again, multiplying by 3, okay, that's all I can do this time. I'll have to leave those numbers. And taking out the x's, that would be 100 minus x minus 4y equals 0. Same again, a product equals 0, so either x equals 0, which it can't, So that means this equals 0, so that means x plus 4y should equal 100. So there's a second condition that must be satisfied. Now, running out of room, taking this equation and subtracting that one, I would have x minus x disappears, 4y minus y makes 3y, 100 minus 50 is 50, so I get y equals 50 upon 3. It's the same thing, isn't it? I had before. 50 upon 3, 16 and 2/3. Which means that if y is 1/3 of 50, x must be, to satisfy this, 2/3 of 50. So x would be 2 times 50 upon 3, that's 100 upon 3, same as before. And feeding it back into this, just putting that as 100, no, it's okay, 50 upon 3, you've got 100 minus 100 upon 3, 2 times that, minus 100 upon 3, that's minus a third, it leaves a third, so you've now got a ninth of 100. Z is 100 upon 9, so that would give you exactly the same answer as you had in that intuitive case. The maximum volume occurs when x, y and z have these values here, and of course that's what they multiplied out to give. Now, when you're doing this multivariable calculus, finding critical points, you have to justify the nature, but that gets a little bit complicated. Essentially, you're having to use, I'll just mention the names, I'm not going to go through it, not for the sake of just this. You have to go through the Taylor series, the Taylor expansion in 2 dimensions, looking at the second order partial derivatives, which in the end form the determinant of a matrix called the Hessian, and then taking the eigenvalues of those Hessian, you can determine whether it's a maximum or a minimum or some undefined one which you might interpret as a saddle point. But as far as this is concerned, just taking it trivially from this little diagram, this little domain that must be 0 all the way around, it must just be like a bubble blowing up over it. So we can take it that that's a maximum. Now there's another way, which relies on thinking of surfaces in space. For instance, this constraint equation, if you look at it, is the equation of a plane. If I was to draw what that plane looks like, just looking in, it's only the positive parts I need, so it's looking like looking down into the corner of a room, the x, y and z axis. How would this plane come through and slice into the room? What portion of that plane would appear in this octant? Well, if y and z were 0, it would go as far as 100. If those were 0, the y, it would intersect there at 50, and if they were 0, then it would intersect that at 33 1/3. So the plane would appear as this triangle in space. Any point on this plane satisfies that constraint equation. You want to find which point on this plane with its x, y and z coordinates gives the maximum value of x, y, z. Maybe I shouldn't be going into all this detail. This business is going to lead to the Lagrangian. But basically, if you were to plot the values of x, y, z in a coordinate diagram, it would just occupy all of space, because every single point in space has got a value of x, y, z. However, if you were to connect the dots, if you were to join all the points in space that had the same product, that would form a surface in space. That's called a level surface. And essentially, to find which point in this plane has got the maximum value of this, you want to find the level surface that just touches the plane. It's going to come in and just touch it somewhere. Wherever it touches it, that'll be the point that gives you the maximum volume. Now, one way of doing that is to say, well, if this surface is coming in and it's to just touch it, it's to touch it like a tangent. So its normal vector would have to be in the same direction as the normal vector of this plane. And that's the way that you used the Lagrangian, equating the normal vector of what's known as level surfaces. Now that means I'll have to construct this as a level surface. Notice how it looks like that just now. Because strictly speaking, x plus 2y plus 3z without being equal to 0 is also a function that fills every point in space. So that particular one, if I put it the other way around, x plus y, 2y plus 3z minus 100 equals 0. That function, it's just the same thing. That's got a value at every point in space. But if I just pick out the points where that all comes to 0, that gives me a level surface. And that's what this is. It's called the zero level surface. So what I really want is, I want the normal to the zero level surface and the normal to these level surfaces when are their normal vectors the same. That's the gradient function that does that. Now there's tons in this, I can't really go into it all. Maybe I shouldn't even say what I'm saying. So we've got these two, now to have them as functions then, these two functions would be this. I've got one function of x, y and z which equals x, y, z. That's the one that I want to optimize, or maximize, well optimize I should say. I've also got another function, call that g of x, which is x plus 2y plus 3z minus 100. And what I want is the normal vector in that to go in the same direction, but it'll be the opposites, as the normal vector in this one. So what I want is the grad, again that's something new, the grad of f to be equal to, and that'll be, since they point the opposite way, some multiple, because they don't need to be exactly the same, of the grad of g, where this is the constraint. Putting them together, the grad of f plus lambda g should equal 0. Now, this new function is called the Lagrangian. The function phi equal to f plus lambda g, or whatever you call them, is called the Lagrangian. And that's called the Lagrange multiplier. But you're not really interested in that. So in this case, the Lagrangian will have 4 variables. It's got an x, it's got a y, it's got a z, it's also got a lambda. And it will be equal to x, y, z plus lambda times x plus 2y plus 3z minus 100. The part you want to optimize and the constraint. So there it is up there. Just pretend we're starting from that. And the condition is what's called the grad of that should be 0, the gradient of that. And that's just found by taking the partial derivative with respect to each of these variables in turn. Each of them should equal 0. So speaking, that 0 isn't a 0, that's actually a vector. So that each of the components equals 0. So that means the partial derivative with respect to x should come to 0. So differentiating with respect to x means take everything else as a constant, would be yz plus, now that whole lot just comes to 1, so plus lambda. That should equal 0. The partial derivative with respect to y, I don't think I'll put the equals in anymore, would be xz, but plus 2 lambda. Ooh, I'm going to have to read that. The partial derivative with respect to z would be xy, but this time it's plus 3 lambda. And the partial derivative with respect to lambda would be all of that. X plus 2y plus 3z minus 100 equals 0, which notice is just the constraint equation. Now all you need to do is solve that system of equations and you'll get your x, y and z for the maximum or for the optimum value. That's the process of Lagrange multipliers. Just forming this combination equation of the thing that's to be optimized and the constraint. Well, what have we got? Well, you can make them all into x, y, z's by multiplying as appropriate. So if you took equation 1 and multiplied it by x, and equation 2, I'd actually want to subtract it the other way around, wouldn't I? And multiplied it by y, so y times 2, and subtracted them, I would have multiplying by x, that's x, y, z, multiplying by y, that's x, y, z, they disappear. I would have 2y lambda minus x lambda equals 0. So taking the lambda out, that says 2y minus x equals 0. The two solutions to that would be lambda equals 0, which I can't have, because if lambda was 0, that means that these things that either y or z would be 0, and you know that the volume would be 0 down on the axis, so that doesn't apply. So I've got this condition. I've got x equals 2y. That's not bad. I could do the same with 1 and 3. If I do 3 times, it needs a z minus x times number 1. So I'll have xyz, they'll disappear. This time it will be 3z lambda minus x lambda equals 0. Lambda times 3z minus x equals 0. Well, lambda is going to equal 0. No, it won't. So that means x equals 3z. Pop them into 4. And what do we get? Well, we've got x plus, now, 2y, which is what I've got, is another x. 3z, which is what I've got, is another x. See where it's all leading? 3x is 100, so x equals 100 upon 3. Y is going to be half of that, so that's 100 upon 6. Z is going to be a third of that, so that's going to be 100 upon 9. Same as that very first intuitive one. Except that was a proper technique for optimizing constraint equations. There are further things you need to do. You have to consider boundary values, but we've already looked at boundary values here. It was always 0 around all the boundaries, because it is an optimization problem. And optimization problems don't just concentrate on the critical points, the stationary points. You also have to consider what happens out at the boundaries as well. Well, hopefully it's simpler next time.